Hi guys, this is Steph. I had problems numbers 3b and 3c on homework 11. So 3b says if A is a member of G, with the order of G is less than infinity, then the order of A divides the order of G. So we're going to start with let A be a member of G and let the order of G be less than infinity. So by homework 5.4, for any group element A, we know the order of A equals the order of the cyclic group generated by A. So the cyclic group generated by A is a subgroup of G, which is something we've also proven in the past. So by homework 11.2, or Lagrange's theorem, the order of a subgroup divides the order of the group. So we know that the order of the cyclic group generated by A divides the order of G. We also set up here that the order of A equals the order of the cyclic subgroup generated by A. So we could just replace this with this since they're equal, and therefore we know that the order of A divides the order of G. So part C said if the order of G is prime, then G is cyclic. So we're going to start with let G be a group whose order is a prime. We'll call it P. So that implies that the order of G equals P. Since the order of G equals P, which has to be greater than 1, because the smallest prime is 2, there exists an A as an element of G such that A doesn't equal the identity. So basically we're just saying that there has to be some element in G besides the identity element. So, as we've proven in homeworks past, the cyclic group A generated by A is a subgroup of G. So, by homework 11.2, also known as Lagrange's theorem, the order of a subgroup divides the order of the group. So we know that the order of the cyclic group generated by A divides the order of G. And since the order of G is prime, we know that only two things divide it, 1 and whatever the order is. We also know that the element A doesn't equal E, so the order of A can't be 1. So this can't be 1. Therefore, the order of the cyclic group of A generated by A, must equal the order of G. So, therefore, if the order of G is prime, G is cyclic. That's it.